Today's topic is an introduction to light. Unlike physicists, chemists, and biologists, astronomers cannot directly experiment with our subjects of study. Instead, we can only look, observe. Our only data is light. Now, there are exceptions to that. Moon rocks brought back from the Apollo landings, meteorites, and we've sent a few probes out, rovers on Mars, things like that. But for the most part, astronomers are limited to using light from afar. And we can't manipulate our objects of study. So it behooves us to know as much about light as possible so that we can extract from it as much information as we possibly can. So our topics for today are just to talk about what light is and some of its basic properties. So electric and magnetic fields. Before we talk about light per se, I just want to mention you've probably heard of electric fields, you've heard of magnetic fields, you've probably played with magnets at some point in your life. So some particles, a lot of particles, have a property that we call electric charge. And electric charge, if you think about it, is kind of mysterious, but nonetheless, if you have two objects, let's say some socks that you pull out of the dryer, and they have a charge, they can attract each other or repel each other. And so we say that a charge creates an electric field around itself. The entire field of chemistry is about electric charges, and that electrons are held around nuclei because of the opposite charges. Electrons are negative, protons in the nucleus are positive. That holds atoms together, electrons in orbit around the nucleus. But electric charges also hold atoms together to make molecules. So chemistry is all about electric charges. And then there are things called magnetic fields, and magnetic fields can exert forces on magnetic poles, and can also exert forces on electric charges if the electric charge is moving relative to the magnetic field. And so those are electric and magnetic fields. Why did I digress into that? Because light is an electromagnetic wave. So if you ever hear the phrase electromagnetic radiation, some people hear the word radiation, they freak out. Electromagnetic radiation, that phrase is just another word for light. And so what light is, being an electromagnetic wave, is it's a combination of both electric fields and magnetic fields together that are wiggling and supporting each other. A changing electric field actually creates a magnetic field. The changing magnetic field creates an electric field. And they support each other in that way as they travel, as they propagate. And once the light wave is created from some source, say a light bulb or a star, the existence of the light wave continues even if the light bulb is turned off. So waves have certain properties. So you may have heard of these words: wavelength, frequency, and speed. Wavelength, normally we use the Greek letter lambda to stand for wavelength. It's the distance of one peak or crest of the wave to the next. Frequency is if you stand at one spot and the wave passes you, it's how many of those crests pass you per second. And the usual unit for that is the hertz, abbreviated Hz, which just means cycles per second. In fact, if you get an old radio set, the dial on the radio may be labeled cycles per second or CPS rather than hertz, but they're the same thing. And then light in a vacuum in space, light travels at a certain speed that we could use V for. We use V for speed, but we can also, in the context of light, we usually use a lowercase c for the speed of light in a vacuum, and that's equal to 3 times 10 to the 8 meters per second, which is really, really fast. That's about 186,000 miles per second, or 300,000 kilometers per second. And there's a relationship between C, lambda, and F. C is equal to lambda times F. I usually kind of explain that equation, why it is that, by thinking in terms of an analogy with walking or running. So if let's say you're walking and your length of your stride is 2 feet. That's like lambda. That's like a wavelength. Each step you take is 2 feet, and frequency is how many steps you take per second. So let's say each step is 2 feet. That's your wavelength, and you take 3 steps per second. Then you're going to cover 6 feet every second, because lambda, your stride is 2 feet, but you're taking 3 steps every second. So c is equal to lambda times f for light. So here's a quick question for you. A local radio station, 98.7 WSMW Simon, the 98.7 on the radio dial. Do you know what that represents? Here are your choices. Give it a thought. Hit pause on the video if you'd like. But when you listen to a radio station, the reading on the dial, it is, in fact, they're giving you the frequency of the radio waves in units of megahertz. So a typical radio station FM radio station has a wavelength in the neighborhood of 100 million vibrations per second, cycles per second. So follow up to that question then, if the frequency of that radio station is 98.7 megahertz, what is the wavelength of those radio waves? The wavelength of those radio waves, lambda. You may need to do a quick little calculation. Feel free to grab a calculator if you want. And although you don't need it if you round to 100 megahertz, and you can do the math without a calculator. But hit pause. Okay, and you're back. The answer is about 3 meters. Here's my written out solution for you. Again, hit pause if you want to look at it carefully. Okay, next a couple of properties of light or light waves. And so first off, I want to define just a couple terms. Energy, you've talked about energy in various science classes. Over the years, we're going to use E to represent energy, and the usual unit to measure it is the joule. Next is power, which astronomers often call luminosity. So if you've had a physics class, you probably called it power. A lot of people use the word wattage, but astronomers will use the word luminosity. Power or luminosity is the energy per time, the rate at which energy is being used. And so a rate is always divided by time, per time, and so it would be joules per second. Now the joules per second has been renamed a watt, and that's why some people, instead of using the word power, will use the word wattage. So luminosity, power, wattage all mean the same thing. Next is intensity. Intensity in the context of light is called brightness. So you may hear the word intensity, you may hear the word brightness. It's power per area. So if I have a light bulb, I didn't come prepared here with this. Now this is not on, but if I have a light bulb, this light bulb is a 100 watt light bulb. And if it were on and I put it right in front of my face, then it's really, really bright, annoyingly so. But if I have it a few feet away, it's still kind of bright, but not so annoying. And if it were 100 yards away, 100 meters away, yeah, I'd be able to see it, but it wouldn't be annoyingly bright. It would just be a point in the distance. So, but no matter where I have it, it's still a 100 watt light bulb. It's still putting out a power or a luminosity of 100 watts. But if it's right in front of my face, that 100 watts of light is spread out over a small sphere surrounding the light bulb. And whereas if it's farther away, or really, really far away, then that same 100 watts of power is spread out over a humongous sphere. So the amount that enters my eye, is very, very small. So we can mathematically relate those with this equation right here, that the intensity, also known as brightness, so some people use a B here for brightness, I'm using an I for intensity, is equal to the luminosity over 4 pi r squared, where r is the distance from the source. And that's because, if you remember from geometry class, the area of a sphere is 4 pi r squared, r being the radius. So it's the radius of the sphere. So L over 4 pi r squared is equal to I. Some people will use a D instead of R because it's the distance from the source to where the observer is. So you'll see this in different forms, but it's always the wattage, luminosity, or power divided by the surface area of the sphere, 4 pi r squared or 4 pi d squared. So what this equation is saying is that intensity is inversely proportional to distance squared. As you get further from the light source, the energy is spread out over a larger distance. So I'm going to back up in here and just look at this diagram here. What this is meant to illustrate is that as you move further away, if a source of light is here, luminosity, at a distance r, it'll have a certain intensity. At twice the distance, that this wedge is twice as wide, but it's also twice as high. You have 4 times the area, so the power is diluted, spread out over a 4 times larger area. So if you double the distance to an object, say a star, its brightness or intensity drops by a factor of 4. If you triple the distance, my webcam here is blocking it, but it has 1/9 here. It becomes 1/9 as bright if you triple the distance. So here's a quick question. Again, hit pause if you want to think about this, but here's the question. How does the brightness of the sun as viewed from Pluto, whose orbit has a semi-major axis of 40 astronomical units, how does the brightness of the sun there compare to its brightness seen from the Earth? And there are your choices. Hit pause, and you're back. It is 1,600 times fainter, or 1/1600th as bright. The distance is 40 times greater. You square that, and 40 squared is 1,600. So if you were standing on Pluto, the sun would appear, you'd be able to see it, obviously, but it would appear simply as the brightest star in the sky, but not so brilliant as it is here on the Earth. And the last thing here, there's a lot on this slide. This is a diagram showing the entire electromagnetic spectrum. The different colors of light have different wavelengths, and then there are colors of light beyond the visible spectrum. So here, the visible spectrum goes from violet to red or red to violet. You can remember the colors by thinking of Roy G. Biv, red, orange, yellow, green, blue, and violet, ranging from 400 to 700 nanometers in wavelength. But shorter than violet, beyond the violet, ultraviolet is the term, is UV or ultraviolet. Even shorter wavelength are X-rays. Even shorter wavelengths are gamma rays. On the red side of the visible spectrum, beyond the red or below the red, is infrared. Below that is microwaves right here, and below that, I'm saying below on the diagram, they're actually longer wavelengths. The longest electromagnetic waves are radio waves. So some people will divide the spectrum up and really consider the microwaves part of the consider microwaves part of the radio spectrum. So sometimes you'll see a diagram where it's gamma rays, X-rays, ultraviolet, visible, infrared, radio, and then other people like to kind of break out that border region between infrared and radio and give it a different name, microwaves. So I do expect you to know the wavelength range of visible light, 400 to 700 nanometers. I do not expect you to have memorized the wavelength boundaries between X-rays and gamma rays, or infrared and microwaves or radio waves. But no, visible light is 400 to 700 nanometers. Now, I've been speaking just in terms of wavelength, but different waves also have different energies. So gamma rays are high energy, radio waves are low energy. Gamma rays are high frequency, radio waves are low frequency. I know we talked about that radio station around 100 megahertz, 100 million hertz. Sounds like a big number, but that's actually a low frequency compared to infrared, visible, X-rays, gamma rays, etc.